Any preference?
Oh, you do it today. That's all right.
I can do it. Sounds good. Add a new slide at the end.
You hear about the physicist that got cooled to absolute zero? Yeah, he's okay.
All right, sir, do you have any last jokes before we get started?
I think I'm tapped out.
That was a very good showing. All right, I think there's probably still a few more people following in remotely on Zoom, but I think we can get started while they're doing that. We have quite a packed day today, so I think it's worth getting started. Right, so welcome to day 2. You survived day 1 of Code Astro. Congratulations. Hopefully it wasn't too bad. I think like Sarah mentioned on the Discord, even if you're feeling a little overwhelmed with the material so far, focus on the things, some of the things, all our materials and recordings are online, so you can always come back to it later, even if we're not going at the speed that you want us to go. All right, so day 2, how do I advance the slides? Just a reminder, we have our anonymous feedback form. You can access this through that link right here, and you can give us feedback as often, as many times as you want. We appreciate everyone's feedback just to help us better shape the workshop. We can try to, it's still early on, so if you give us feedback now, we can try to react to it during the workshop, but otherwise we can use it to improve the workshop for future years. And we also just want to remind people about how to do group work for paired programming in particular. In general, you'll see this from a lot of our in-person activity, for our synchronous activities, but also for the project itself. It's a reminder that one person is the driver who's responsible for typing the code, and then the other people are the navigators who watch what gets typed and offers direction to the driver about what to actually type. So the driver thinks about having the right syntax and reminding people that, oh, we have to define this function in ways that maybe the navigator is like, oh, I'm already moved on to the next part of the code, whereas navigator is thinking bigger picture and trying to try to guide guide the whole group into figuring out to completing the task at hand. Like we said, we recommend people to switch back and forth. This is good so that people have chances to do both roles, and that in 3-person groups or larger, just more people are the navigators. Make sure the navigators get along somewhat well, but yeah. And then in general, use Discord or Zoom, share screens to do this remotely. Also, please ask questions. We have many ways to ask questions. You don't have to use all of them, but use whichever ones feel most comfortable to you. You should ask them often. You can ask them in the chat box. We can respond to them on Zoom in the chat box. You can ask them on Piazza or Discord also in real time, and hopefully one of us will be able to answer your question in somewhat real time also. Just to remind people about the goals of this workshop, by the end of this workshop, you'll be able to use the language of software development. You'll be able to develop and release an open source astronomy package, which I've seen lots of people work on already. This sounds like there's a lot of great packages being developed this week. Also, write code that follows the best practices of software development. By the end of today, we have two main learning goals. One is to be able to use Git and follow the Gitflow process to contribute version control code, and also to use to interactively debug your code using breakpoints and not just rely on print statements. For the goals of your project today, we want you to keep working on your project, but also get comfortable using GitHub to collaborate on your project, put all your code on GitHub, and start using branches and maybe start delegating tasks. We're not working on the project together synchronously. We can also work on the project separately on various subtasks. Just a little bit of perspective, the next 2 days, we'll probably talk a lot more. We'll talk about a lot of scaffolding that you will do to your Python packages, like documentation, tests, and releasing your code. So today's a good day to make progress on the main functionality of your code because you'll probably be busy in the next 2 days adding some of the scaffolding stuff. As always, we've been making a few updates to the code, mostly minor updates, but just to check, always update the code Astro repo, do a git pull, git checkout main, and we'll talk a little bit about what those mean today, and just update your code to the most recent feature. And also for everyone here, we're going to try to get a group photo at the end of today's synchronous session. So at noon Pacific time, about 3 hours. We'll do the Zoom one first here, right after the session ends. And then as long as it's not actively thundering outside, we'll probably have the in-person people will go outside and take one without our masks on. And then we'll somehow Photoshop the two together. And maybe people who are good at Photoshop can find interesting ways of doing that. But just remind everyone, stick around at the end of our session today. Don't leave immediately. We like to get some of your smiling faces, especially to our funding backers, the Heising Simons Foundation. We like to see lots of people enjoying this workshop, and hopefully they'll keep funding us in future years as they see lots of people who are appreciating our Code Astro workshop. So just a reminder for people to stick around and do that. And also one brief minute of in-person logistics. Sorry, Zoom folks. We're gonna assign rooms this afternoon for people to work in the on your project groups together. This is to minimize the TAs going up and down the floors. I know that some of them like the exercise of going up and down floors, but just to minimize that, we're going to put all the people work with one TA in like the same room. And we have, I'll talk about that at the end of the workshop today. But the room assignment's already on the group pairing spreadsheet that you have access to. And also, if you haven't taken your COVID tests and recorded them to either Sammy or Simon, please do that soon. Okay, so I think that's everything for the welcome slide. So let's get started on today's workshop.
Can I just add one thing real quick?
Right. Yes.
So some of the groups have been updated a little bit since yesterday. This always sort of happens on the first day because there's a lot of stuff going on. So make sure you check the spreadsheet again, make sure your group hasn't been updated. I'll post it in Zoom for those in Zoomland, and I'll also post it on Discord. So make sure you just check it at some point today. Make sure your group members are still who you expect.
Great, thanks for reminding me on that. Okay, so let's get started on Git. No pun intended. Okay, so yeah, let's talk about Git. So first, I'll just start out with talking about briefly about source control in general. Source control is this concept of kind of keeping track of your code as the history of your code as you're developing it. There are many ways to do source control. There's a basic way of source control is just copying your entire folder you're working on. It's like making an old version of the folder and just pasting it. That's totally a version of source control. It works. It may not have the granularity you want, but it's still a version of source control. There are a lot of, nowadays there's a lot of tools that have been developed to kind of keep track of your files as you develop them. You might have heard of some of these, like Git, SVN, Mercurial, Team Foundation, things like that. But even things like your cloud storage services like Dropbox and Google Drive are also versions of source control. You can see for a lot of them, you can actually access previous versions of your files, and every time you sync them and things like that. So that's actually not a bad way to do source control too. Today we're going to talk about Git because it's the most popular in astronomy software development, in particular open source software development, and that's generally true even outside of astronomy as well. So the motivation to use source control is generally to have legacy versions of the code. Sometimes your code, as code develops and things, as computers develop, like a new version of code may not work on older computers and things like that. So having older versions of the code are useful in that sense. You're also able to revert to older versions. This might be true for if you change a bunch of your code and suddenly none of your code is working anymore, and you're like, oh, why isn't it working now? At least you can revert to your older version. You know that version works, even though it might not have the newest features. It also is good for collaborative work. It's designed in ways so that like many people can contribute to a code package and do that in a way that's as least intrusive as possible. It's obviously hard to have many people working on something at once, but hopefully today we'll show you some tools and some processes in particular to kind of guide how multiple people can work on a single package, at the single piece of code together. Our general recommendation is to use source control anytime you are programming, even if it's by yourself. So just for your research, you can upload your code to a private GitHub, sync it to your Dropbox or something like that. Just keep it updated. Keep it so that you have past versions in case you ever do need to revert. I know, like for me, at least once a year, I have completely broken something where I accidentally deleted something and need to go back to my older version of the files, basically. So it definitely is useful. So today we're going to talk about Git. First, I'm just going to briefly touch on the basics of Git. So here's just a sampling of some of the Git commands that you might encounter. Things like git clone, which copies a repo onto your computer. Git init, which takes a local file folder in your computer and makes it a Git repo officially. Things like git add, which adds changes that you just made to your next commit. Git commit actually physically creates the commit. Git pull grabs new commits from a remote repo and pulls it to GitHub, pulls it from GitHub and puts it onto your computer. Git push takes commits you just made and pushes it to a remote repo like GitHub. Git branch creates a new branch. Git checkout allows you to check out a certain branch or commit given its name that you pass in, and Git merges changes from multiple branches from another branch and puts it into the current branch. It sounds a little overwhelming, and I feel like oftentimes you go and try to look for something and you just get a bunch of these commands and you're not sure what you're doing, but you're just typing them because that's what people on Stack Overflow tell you to type, and it gets the job done. And this is it's kind of abstract, and these are the main Git commands, but sometimes you're like, what's actually happening under the hood? Why am I doing these things? So that's kind of what we want to talk about today, more so than just discussing the details of each of these, instead of more so showing you a bunch of Git commands and a bunch of fancy Git techniques, more discussing what's actually happening under the hood of Git. And the hope is that maybe if you have a mental picture of what's happening under the hood in Git, that you can try to reason your way about what I need to do to get to do what I want to do with Git. So that's more of what I'm going to try to do in the next hour than try to teach you all the fancy ways you can use all of these commands. So I'm going to skip this demo for now. So yes, mechanics of Git. So let's take a second briefly to appreciate the meme as always. Yeah, so as you probably heard from what I've been discussing, Git's sometimes not the most intuitive version control system out there, but hopefully we'll make it a little bit more intuitive today by kind of talking about it from a more physicsy point of view and think about how it functions, what are kind of the main rules governing Git. So I'll just caution that the the model I'm going to discuss here is I made it up myself, so with whatever caveats that is, but also it definitely simplifies the actual underlying implementation of Git. So it's not actually exactly what Git is doing underneath the hood, but it's a useful abstraction or think about what's happening underneath the hood without thinking about all the implementation details of Git. So the fundamental kind of atomic unit of Git is the Git commit, quote unquote. You can think of it like an object, like we were talking about object-oriented programming yesterday. It has a bunch of, this Git commit object has a bunch of attributes. It has the ID. So this is just a random string of numbers. You've seen this anytime if you've made a Git commit, like it gives you, like we've made Git commit 876AB12. You're like, that's nice. What does that mean? But it's just an ID a unique ID to represent it. So that all Git commits have a unique ID basically compared to any other Git commit. It also knows about its parent ID. So a Git commit also knows like what commit previously was created and what that it basically is a change. What is a change from that commit basically. In addition to that, it has a list of changes. So you can see here, maybe we created a new file, input.py. Maybe we also modified a file, plot.py, and we added text on line 12 and deleted text on line 36. So it has basically a list of all the changes you made in this commit compared to its parent commit. It also has a human readable message, such as made some changes to something. This is just like for us to look at, be like, oh, that kind of makes sense for what has happened. It also has a bunch of metadata, things like who made this commit, the email of the person that made the commit. And this is actually quite, Git actually uses this to identify people more so than the actual author name. So the email that you put in is often how they distinguish various Git commit authors. It also has the time of the commit, like when did you actually make the commit. But there's also other things that we kind of skipped over here. But basically, this is kind of the atomic unit in our model. Is this Git concept of a Git commit is a bunch of changes made at one given stage in your development process. And a Git repo basically consists of chains of Git commits, and that basically forms the development history of that Git repo. So let's actually just so we're basically going to do Git by hand, and we're going to run some Git commands to create a new Python package and basically see what happens to the Git commit tree as we make the commits. So the first thing we're going to do is, in this example, we're going to make a package that makes color images and plots them. That's the goal of this package. So the first thing I do is after I make the folder is I type git init. This basically initializes the folder and tells Git that this is a folder that we're being version controlled right now. There's currently nothing in the version control tree, but we've initialized it for Git. If you do something like git clone, this gets basically automatically run, so you don't have to worry about this. So then we actually have to do the actual hard part about developing our code. So we had to go type, and create and add a bunch of code. Let's say we added this to this file called color.py to generate color images. After we made those changes and we're happy with them, we type git add color.py, and this stages the changes to the next commit that we create. So we made a bunch of changes, and then the next commit that we create, we'll add those to that list of changes. And then we can actually physically create the commit. So we do a git commit, and then we do a -m to pass in a human readable message for what is this commit's meaning. So here we just type initial commit. And then if we type this command, we enter, our terminal will return something like this. It'll say main 309f initial commit, one file's changed, create color.py. So this is what we see in our terminal. This is what happens in the git commit tree. So now we have our git commit tree has one commit. Its ID is 309f. Its parent ID is none because this is the first commit of the git commit tree. There's no parent. This is the original commit. You can see it's in its list of changes. You can see we created this file color.py and we added text starting at line 0. And the message of the git commit is initial commit. And there's a bunch of other metadata in it too, but we're going to skip that for now. So we've created one commit. So now let's say we want to, we want to edit the code because we found a bug and we want to fix it. So we go type, add and then basically fix this bug, and then we go add git add color.py. So we made new changes to color.py. We're adding those to our next commit that we're going to create, and then we can type git commit again -m to pass in a human readable message, and again our terminal returns something like main 8A6C fix red color bug. So here, we're looking on the right, we now have 2 commits in our git commit tree. We have our original 309F, but now we have a new commit 8A6C. Its ID is 8A6C because that's its name. Its parent ID is 309F, so I know that it basically is created relative to its parent 309F. And the changes that it contains is that we modify color.py, we added text on line 12, and we deleted text on line 36. And the message it has is fixed red color bug, which is the human readable message we passed in using the -m command. And also notice that I've drawn this arrow pointing from 8A6C to 309F. This is because 8A6C depends on 309F. Its changes only make sense in the context that 309F exists. Notice that 309F doesn't know anything about 8A6C. The object 309F doesn't have any attributes it knows about its children, basically. But 8A6C needs to know about its parent in order for this commit tree to make sense. I'm going to drop the arrows moving forward just to keep these graphs a little bit less busy, but just keep in mind that each commit only knows about its parent commit. So then, we can keep working on this code. Say we wrote a plotting module that lets us display the color image. So we go type, add a bunch of code to plot.py, and then we run git add plot.py to stage those changes, and then we make the commit based on those staged changes and git commit -m added plotting, and so you see we've created a third commit 91E1. Again, 91E1 has a parent ID of 8A6C, and its changes are create plot.py, added text starting on line 0. So now we have a 3 commit chain, and remember that 91E1 only knows about 8A6C, and 8A6C only knows about 309F, and the 309F doesn't know that we've already had a 3 commit chain so far. So we've started creating this tree of our history of our commits. But how do we reconstruct the entire history? So that's kind of where git branches comes into play. So now that we were able to make commits and link commits to one another to kind of make a history of all our changes we made to our Git repository, we can use branches to kind of reconstruct histories or multiple histories. So branches allow us to basically work on separate features in parallel. The base branch or the standard branch is usually called main or master. Nowadays, we mainly use main. Git branches are not actually that complicated in themselves. They're basically just pointers to the most recent commit on that branch. So the pointers is just a computer science term for something that just doesn't contain information, but just, sorry for the definition, or the recursive definition, but basically just points to where the data is. It doesn't actually itself contain the data. It just tells you where that data is located. Your question?
Yeah, so all of this so far is just local to you.
That's correct.
Okay, we haven't brought in the workflow.
Yeah, so the question was, all of this stuff is just local to the computer. We haven't brought in the remote. And the answer is yes, we have not brought in the remote. There's actually not that much. We'll talk a little bit at the end about bringing in the remote, but the remote doesn't add too much to this actual model here. Mm-hmm.
So initially when you showed the thing with color.py, so we did add color.py, committing and including this edit message, and then we're editing color.py doing another thing. So does that create a duplicate file, or how does that work?
So the question was, we edited color.py twice, once in the original commit and once in the second commit. Does that create a duplicate file, or how does it work? So in our mental model, in our model here, we basically are just adding modifications to the code. So it's not like it's creating a separate file. It's just like we're adding each of these git commits has just the attribute of what has changed between this file and this commit and the previous commit. So you're basically tracking a list of delta changes.
And so to sort of add on to what Rebecca asked, how do we make sure? So when you say this folder, is it like the working directory folder, or how? Like I guess I'm just having a hard time sort of translating between what how Git structures folders, how like our local computer structures.
So the question is, how is Git structure folders versus how local computer structure folders? It's the same. Git just uses your local structure, folder structure. It doesn't do anything fancier.
Oh.
I'll note that I said that we're just in our model, we're just basically everything we change is just a list of changes. We're not like making new files and things like that. This is where the model breaks down. The actual implementation of Git does actually create a copy of your file every time you change it, but it is very confusing, so we're not going to think about it basically. But when you interact with Git, you basically, if you think of it as just adding changes, it basically works for almost all use cases. Okay, was there any other questions? I see there's a bunch of things in the chat, but I don't have time to read them.
I think we're good. We've been discussing.
Okay. All right, so let's continue on branches. So if you bear with me a bit, hopefully branches will start making sense. So basically, a Git branch is just a pointer to the most recent commit on that branch. So here in our example, we have only just the main branch, because that's the default branch that gets created anytime you create a Git repo. The main branch points to 91E1. So you can see that the main branch points here. And because 91E1 knows about its parent, we know that 91E1 was created from 8A6C, and 8A6C knows about its parent, so we know that 8A6C is created from 309F. And by working backwards through the history, we can basically track the full history of the main branch by just going from the most recent commit and working our way back to the first commit in our Git commit tree. There's also this concept of a head pointer. A head pointer is just like another pointer in our list of pointers. And the head pointer points to what current branch or current commit that you're currently working on, like from. So the head pointer right now by default is saying that we're on the main branch, and the main branch is on 91E1. So the head pointer, which is where we're currently working from, is pointed at 91E1, and the main branch is also pointed at 91E1. You'll see how this changes in just a second. Was there a question in the chat? Sorry.
You might have a couple questions going back and forth.
You gonna answer everything? Okay, great. I just saw some question marks appear, and I was like, okay, I'm gonna keep going and just like yell at me if there's something I should clarify. Okay, so why do we have both the main and head pointers? So this is where they start kind of making sense, hopefully. So let's say I want to make a second branch. I want to make I want to add interactive plotting to my color image making module. So that we can adjust the coloring of the images by eye. We don't have to like do it all through code. We want to make it interactive. So we want to make a new branch to do this work because we don't want to break the working code that's already working at the current branch. So we do something like git branch plot upgrade, and this creates a new branch called plot upgrade. But if we type something like git status, it'll show that we're still on the main branch. So what has happened here is that the git commit tree has not changed at all. But if you see in our list of pointers, we now have a new pointer. So main is still pointing at 91E1, but now we have a new plot upgrade branch that's also pointing at 91E1. So both of these branches have the same commit history. So the commits, so the versions of the code look exactly the same. And our head pointer is still pointing at the main branch, which is at 91E1. So that's still where we're currently working from. Now we can switch that new branch by typing something like git checkout plot upgrade. And this basically moves us to the plot upgrade branch. And then if we type something like git status now on our command line, we can see that we're now on the plot upgrade branch on our command line. So here you can see that, again, the git commit tree has not changed. We have not edited any of our code. We're just making branches, basically organize how the code, organize organize how we're going to work, basically. Again, so the main, everything's still pointing at 91E1, but now you can see that the head pointer has changed. The head is now pointed at the plot upgrade branch, which is still conveniently pointed still at 91E1, but it's going to follow the plot upgrade branch from now on instead of following the main branch. Now, so now if we actually make some edits to the code, let's say, let's actually do some hard work, we do some work and actually add interactive plottings. We go type, and then we make those, save those changes. We git add color.py, git add plot.py. So we've staged changes to both the color.py and plot.py modules. And then we can make a commit that that commits both of those staged changes. So we do a git commit -m with a message. And you can see that we've created a new commit 353b. So now our Git repo looks like this. So in addition to 309F, 886C, and 91E1, which main is pointing to, we also have 353b. So this is a fourth commit in the commit chain. I've drawn it slightly ajar to the right, and you'll see why briefly. But basically now our plot upgrade branch is now pointed at 353b. And our head pointer, which points to the wherever plot upgrade is pointing to, is also pointing at 353b. So we're currently working from 353b, and that's also on the 353b branch. So currently the main branch doesn't know about 353b at all, because remember that our parent commit, like now on E1, knows nothing about 353b. So the main branch only knows about this series of 3 commits, but the plot upgrade branch knows that we've actually added this fourth commit to this tree. So like in theory now, if we deleted the plot upgrade branch, we would know, and only the main branch remains, we will know nothing about this new commit that we just committed, basically. So let's say, in the process of doing that, we also figured out that we made some bugs, we had some bugs in the original code. So like we had some coloring with nan pixels messed up. We should fix that. But we want to fix it now on the main branch, for users on the main branch before we fully merge in our changes of the interactive plotting code. So then what we can do is do git checkout main. That'll put our head pointer back at pointing at the main branch. So if we do a git status, it'll tell us that we are on the main branch. So then we can make edits to color.py, and then we can do a git add color.py to stage those edits. And we make a git commit. And now we've created a new commit on main that's A329. So here, now we have a new commit, A329. Our main branch is now pointed at that commit. That's the latest commit in that branch. And our head pointer is pointed to its main because we did the git checkout main here. And the head pointer is also pointed at A329 because that's the latest commit in the main branch. So here, if we track the history of the main branch, A329's parent is 91E1, 91E1's parent is 886C, and 886C's parent is 309F. So that is the entire history of the main branch and all the changes that have been made to the main branch. Whereas if we look at the plot upgrade branch has stayed the same from before. It's still 353b, going to 91E1 to 886C to 309F. So here we have divergent histories, but both histories you can trace back to the original commit themselves. But they, again, don't know nothing. They don't know anything about each other. They just know about what changes went into their own branch. So then, after we got the interactive testing plotting working, we want to merge these changes back into the main branch. So then we want to do a git checkout main. Well, we happen already to be there, but we can run it again just to be safe. Do a git status. It shows that we're on the main branch, and then we do a git merge plot upgrade, and this will merge the changes in the plot upgrade branch into the changes into the current state of the main branch. So it's going to merge the commits from 353B into A329. And when you do that, you make a merge commit. And this merge commit, if there's no conflicts, will basically just automatically be created when you run git merge plot upgrade. So git merge plot upgrade will automatically create a merge commit. So now we have this new commit 8443. You can see it's a little bit different because it has basically two parents. It says we're merging changes from 353B and merging them into A329. And we're basically the changes that we merged in are from a following list of changes here, which I'm not gonna that we're not gonna write out. But basically, then it's gonna have an automated message that's like merge branch plot upgrade, and that happens automatically when you run git merge plot upgrade when there's no conflicts. But what if there are conflicts? So in the case, let's pretend that we got this far, but here instead of there being no conflict and this merge commit being automatically created, what happens if there are conflicts? So then our terminal output will look something like this. It'll be like in all caps conflicts, merge commit in color.py, this very ominous sounding thing. So our edits, basically that means our edits in 353B and A329 to the color.py file conflict, and the basically Git doesn't know how to automatically merge them together in a self-coherent way without actual programmers thinking about what do these changes mean and how do we merge them together. So one example of that happening is something like this. So let's say, in our plot upgrade branch, when we were making interactive in our color.py file, we had maybe a file that's called like 2png, and we added in this new keyword called interactive, and we set it to false by default. And maybe at the same time, when we're fixing the nan bug in the main branch, we also added this new keyword to the same function on the same line that's called like mask nans equals to false. So basically, we modified the same line of code in both commits, and anytime that happens, Git generally doesn't know how to merge two lines of code that are different. That requires actual programming, not just source control, basically. So when that happens, it's basically being like, there's too much. This is too confusing, you go figure it out. So it'll basically tell you there's a conflict, and it'll make something like this. It'll write something like this to the text file. So when you run git merge plot upgrade, your new color.py file will have a few extra lines that get automatically added into it. It'll have something like this, a bunch of left arrows, head, and then one version of this line 99, a bunch of equal signs, a second version of line 99, and then a bunch of right arrows. So basically it's saying that the plot upgrade branch looks like this bottom portion, and head, which is on the main branch, looks like the top portion. And basically it's asking you, all right, this is the difference. Please figure out how to fix it yourself. So we have to basically manually fix this. VS Code does have some nice high syntax hiding. If you ever see any Git conflicts, it will basically highlight them and give you options for how to fix them, basically. So there's some nice things in the text editor for doing that kind of stuff. So we gotta have to manually fix this ourselves. There's no automated way around this. So we can say like, we look at this and be like, it's pretty easy. We just make both of them keywords on the same line and everything is happy again. But this is something Git doesn't know how to do. We have to do this ourselves through manual code editing. So then if we go back to our Git tree, this is what it looks like. So after we get our conflict, we have to manually make those edits that we just saw before. And then after we make those manual edits, we have to do a git add color.py to stage those manual edit changes that we just made. And after we did that, we can create a new commit. And actually, usually generally Git will give you a suggested Git commit message of merge branch plot upgrade or something like that. And again, we can create a merge commit 8443 that merges changes from 353B into A329. So the Git commit tree actually looks exactly the same. It doesn't know that we basically ran into a bunch of conflicts and that we had to fix those conflicts ourselves. It just knows that you merged this commit A353B into A329 and all the conflicts stuff is happening in this changes attribute basically. So the commit tree itself doesn't really care about the conflicts. The commit tree will look the same. All that conflict stuff happens underneath the hood in this. Okay, so that's basically everything I wanted to start off with in our like mental model of Git. So for the next 25 minutes or so, I want to get people some practice into practicing Git themselves by hand. So we're gonna basically do a few situations, and we're gonna try to draw out what the Git commit tree looks like. So the first activity is, let's say this is on the right, this is the current state of the branch on our computer. 91E1 is the latest commit, and we run git pull to pull updates from the remote, say GitHub. We run git pull to update changes from GitHub. What I want you to do is draw out what happens to our local Git commit tree in each of the following scenarios. If the remote branch, the one on GitHub, is ahead by one extra commit, 832E, and another situation where the remote branch on GitHub has 3 commits, but the last commit, the third commit, is 832E instead of 91E1. So draw up those by hand. If you get confused, you can always make a test repo and actually just test them out. Making repos is basically free nowadays, so you can see what happens when you do this. The second activity is, oops, I actually committed something. It's totally wrong in 91E1. I want to undo this. This is bad. So there's 2 ways to revert these changes. So there's 2 commands you can use. One is git revert 91E1, and the other one is git reset --hard 8A6C. So what I want you to do is try to learn about what these 2 commits do online, and try to draw out in your mental Git commit tree model what happens to the Git commit tree in both cases. Let's do this in our project groups, or for the in-person people, you can pair up locally with whoever's around if you want. Designate one person to be the recorder, the person that actually writes down the answers. You can do this in like PowerPoint or Google Slides or like Zoom whiteboard or anywhere, or a piece of paper, anywhere you can draw out some of these git commit by hand. I'm going to post a Piazza post, and like you can take screenshots or pictures of your images and post them as your answers on the Piazza post. Definitely try to do activity 1, and then if there's time, do activity 2. Like I said, you have 25 minutes, so it's 9:45 right now. So we'll end 10 minutes after the hour, so 10:10 California time. And for people on Zoom, we'll enable breakout rooms and go to the breakout rooms of your project groups. Is there any questions about any of that? Okay, if not, let's break out into groups and work on these. All right. So let's briefly go over the answers. So it looks like people have made some progress. There are a few misconceptions I think we should go over, but this is why Git is confusing. Let me share my screen again. All right, so this looks like just a reminder for activity 1. We had the current state of our branch, and we want to do a git pull from GitHub. And what happens if the remote branch is ahead by an extra commit, or the remote branch also has 3 commits, but a different third commit than our local branch. So here's the answers from group 11. This one looks pretty good. So if the remote branch is ahead by an extra commit, then when we do the git pull, then our local commit tree also gets this extra commit added onto it. Basically, they get synced together, and we have this new extra commit 832E that is a child of 91E1. So that one's pretty straightforward. If there are, however, in the case there's conflicts, if the if we are at 91E1, but GitHub is at 832E, what happens is something like this, where we basically have to do we basically get a separate branch on our local tree, and then we have to merge them. And it's correct that if there's conflicts, this doesn't automatically happen. But if there is not conflicts, then basically we basically create a new merge commit automatically, and our head pointer gets automatically incremented to this new merge commit, when we do a git pull. So in this case, basically the remote GitHub branch is treated as basically like a separate branch of our commit, like the remote version of the same branch is effectively a separate branch that we've synced into our local version of this branch. Activity 2 is a little bit trickier because we didn't tell you what these commands do, but we asked you to try to figure it out. This happens when you're using Git, so it's kind of why we wanted to practice this. So what do Git git revert and git reset -- hard do? So I think people were pretty close, but there are some subtleties. So let's show you the answer key version. So if you do a git revert of 91E1, you don't actually move your head pointer back, or things don't get deleted or anything. What actually happens is you create a new commit, which is a revert commit. And what this does is basically undoes the changes in 91E1. So it's like a commit and an anti-commit, and they collide, and all those changes disappear into the ether. So basically, this new commit 3BC7 is basically a commit that undoes the changes in 91E1. So the state of the code looks exactly the same as if you're in 8A6C, but you don't actually go backwards. And when you do most Git commands, unless they are very specific ones, you generally only append to the command tree. So you have a full version history, including a history of all the reversions that you've done. And this is generally the recommended way if you want to revert something, to do it this way. In very few cases, you might want to run git reset -- hard. And what this does is basically forcibly moves the head pointer back to 8A6C. So if we are so our current state of the branch is of this branch, which I assume is the main branch, basically points to 8A6C. So this is 8A6C 309F, and all knowledge of 91E1 is lost into the ether. This commit still exists on your computer somewhere, but nothing links to it, so you basically cannot access it through the normal Git process anymore. So that's kind of what happens in these two cases. And generally, like I said, you want to use reverts. This is a very special case. You generally try to avoid doing something like -- hard. Yes, questions?
So, just to make sure I'm understanding, if you're at the last one, I think so if you revert, so are we, wait, so we were at 91E1.
That's right. So previously we were at 91E1, but we want to undo the changes of the 91E1 commit. So when we ran git revert 91E1, what happens is that it creates a new commit 3BC7 that basically undoes all those changes.
But is it identical to
So the state of your code is now identical to 8A6C. It's basically like I said, it's a commit and anti-commit. They just collide, and
so you could technically return to 91E1 if you check.
Yeah, if you do a git check on 91E1, you can actually revert to that version of the code still. So the main principle of Git is, in source control in general, you want to track all your history, even if it's undesirable history. In very, very few niche cases do you want to actually delete your history. Typically, that's when it's like you only want to delete your history when you accidentally type your password into the code and commit that. You want to delete that. You don't want your password in the source control history. But otherwise, you generally want to just do a git revert. Okay, so we'll post these solutions on the GitHub in the Code Astro Day 2 GitHub repo. So it'll be here later today, so you can look at these more also. In the meantime, let's take a break, say maybe a 13-minute break, and we'll come back at 30 minutes after the hour, so 10:30 a.m. Pacific time. So yeah, let's take a 13-minute break.
Just also want to make a quick announcement regarding the breakout rooms, which is that if you end up in a breakout room by yourself and you want to work with someone else, you should feel free to move around. So feel free to go to another room. You should be able to jump between rooms. Okay, so first I just wanted to remind you how to access the materials and get to the lesson I'm going to show you. So you can do code Astro GitHub, just Google it. It's the first thing that comes up here. And then for each day, you can just click on the day, the folder for the day, and all the relevant links will be down here. So all of the presentations that you see, we've got the slides linked here. So Jason's activity will be here. We'll also post the answer key later today. So I'm going to talk to you about Gitflow. So the slides are here. Alrighty. Sweet. So before we get started, I just want to say a lot of this material is sort of repeated what Jason said, just in a different way. So if you hear the same thing twice, don't worry too much about it. It'll help to hear it twice, I promise. I'll have some different analogies and different sort of focus for the lesson. So this lesson is more going to be about the mechanics of implementing Git for using your in your actual projects. So it's going to be less about the conceptual, like how can you imagine how Git works in your head so that you have a picture of it and help you understand when things go wrong. This will be more about like, what's the actual way, what does a Git flow look like? So Git flow is a particular way of using Git and GitHub in order to source control your project. So I'll get into that. So the goals for this lesson, by the end of this lesson, you're going to be able to create a Git repository, make a pull request consisting of multiple commits, and define Git flow and give examples of its advantages. So the structure of this lesson is in the bottom here. I'm going to first do a quick overview of committing code. I'm going to give you a demo of how I actually commit code in my own workflow. Then I'm going to give you a conceptual walkthrough of how Git flow works. And then finally, I'll do a demo of actually using Gitflow. So the Gitflow demo will be sort of a type along type situation. So especially if you followed the Gitflow conceptual walkthrough really well, I would encourage you to type along with the Gitflow demo. If you were sort of confused with the Gitflow conceptual walkthrough, I'd then encourage you to just sort of pay attention to the Gitflow demo and focus on why I'm doing what I'm doing rather than trying to actually follow it yourself. All right, so I'm going to go back to the beginning a little bit and talk about how Git works. And I'm going to give you two analogies. The first is like a time capsule. Oops. So commits are like points in the code that you can revisit. So every time you commit your code, it's like creating a time capsule so that if you want to Git check out that particular commit, you can go back to exactly what your code looked like there. So there was a question in the last lesson about how often should you commit your code. And it's sort of helpful to think about it in this light. Like if there's ever a point that you want to revisit in your code, it's useful to make a commit. It's generally better to make more commits than fewer commits. But there's also a crossover point, like you don't want to make a commit every time you type a single character. You want like sort of chunks of information that you've added to your code that you can then go back to. The next analogy is the more about the process of committing your code and the processes that you have to do in order to commit your code. And the analogy here is that the process of committing your code is like the process of making a scrapbook. So when you're making a scrapbook, you first take pictures, you then lay them out, and then you glue them down. So taking pictures is like making changes to your code. You can take lots of pictures, or you could just take a single picture. Laying them out in a scrapbook is like staging the changes. So this is the git add command, which tells Git which changes you want to commit whenever you actually press that button and commit. And then the third step is gluing them down. So that's like committing the changes. So you can keep both of these analogies in mind as we go through the rest of the presentation. And one of these analogies I stole from this excellent article up here. Okay, so I'm going to give you a quick demo on committing code. This is sort of a repeat of something that Jason showed you, but I want to show you how I commit code in my own workflow. Give me 1 sec. Share my screen. Okay, so here's a blank VS Code window. I'm going to open up a test repo that I made for this lesson. I'm going to put it on my desktop. Yeah, so I'm opening up my repo. This is my little script, which is the only thing in this repository. It's got 1 line in it, hello beautiful world. So I'm going to now make a change to this and commit that change. So let's say I want to, let's say I really like the world today, and I'm going to say print hello extremely beautiful world. It's not just a beautiful world. Okay, so if I click this source control tab up here, you can see that there's now a list of changes. My little script is listed here. You notice if I actually take out the beautiful, it'll undo that change, even though I've saved it on my local computer. Oops. Hello, extremely world. Beautiful world. So now there's no changes because it's exactly the same as the last commit in the log. Extremely beautiful world. I'll save it. The changes show up here. So now the first thing I'll do is I'll add those changes or stage the commits. So remember, that's like the process of laying out all of your changes in the scrapbook. And I do that using this little button here. The plus button on the top is stage all changes. You can also stage by file. So if I click this plus, it just adds or stages the changes for this script. If I do the one on top, it does it for all of the files. Okay, so now everything's laid out. Now I want to glue it down. So in VS Code, you can type your source message here, your commit message here. So I'll say added extremely. Should I spell that right? Doesn't matter. Added extremely to message in my, I don't need to say in my little script because it'll show it. Now I press this little check mark in order to commit it. All right, and that's it. So I've committed the change. Now we can see that change if I do git log in the terminal. So now you can see my commit ID. You can see where the head is pointing, and you can see all the previous commits that I've made as well. So if I wanted to go back to one of those, I could use git revert, or if you're feeling really crazy, you could do git reset to go back to either of these. All right. So that's how I commit code. I also want to say too that I'm showing you in this lesson my own workflow. This is definitely not the only way or even the best way to commit or manage source control. I do a sort of combination of terminal and VS Code buttons or commands for my own Git workflow. You have to find out what works best for you. Okay, let's go back to the slides. Cool. So we now know how to commit code. Why do we need anything else? As Jason hopefully convinced you in the last lesson, it's really helpful when you're working on big projects with lots of people committing code at once to use different branches. Source control in general allows people to edit the same code base at the same time. So if you create different branches, several different people can be working on even the same parts of the code. And you have a really nice way to add all that code back together in the end. Okay, so now let's get into Gitflow. So Gitflow actually has a specific definition. It's a particular way of using Git and GitHub. Some of the advantages of Gitflow are that it allows for multi-user development and testing. So that's what I said, like you can have several people working on different branches at once. It also protects the main code. So it makes sure that you're never releasing a version to your users that is maybe untested or has some conflicts in it that haven't really been worked out yet. It's also easy to go back to a stable point if something breaks. And you can perform work in parallel on one or more feature branches. Okay, so before we go on, I want to have everyone help me fill out this vocabulary list. Some of these I haven't explicitly defined yet, but I am confident that given the vast knowledge in this class, collectively, we'll be able to figure it out together. I also want to remind you about the overall vocabulary list that's at this link here. Yeah, okay, so I was imagining that I'd be in person when I did this, so I'm gonna have to do this a little bit differently. So the way that I'm gonna do this is using Stack. So if you've not used Stack before, the way that you do it is when you want to say something in Zoom, you just type Stack, and then I'll call on the first person that says Stack in order. So if you're in person, I think the way that we can do it is you raise your hand and then Jason can add you to the stack and then just come up and speak into the computer. Okay, so we want to define all of these things. So let's get started. If you have a thought about how to define one of these, type stack. I'll call on you. You got this, y'all. I believe in you. All right, code Astro.
All right, we got two, so you want to come up first? You want to come up to the computer first? Sorry, we got, otherwise the microphone.
Thanks so much.
For clone, a repository copy linked to the remote repository.
Awesome, thanks. So I'll say it's a local repository copy that's linked to the remote. Awesome. Another in-person stack?
Yeah, so for commit, I was thinking it would be a change that creates an additional node to the current branch.
Awesome. Change that adds unit to current branch. Awesome. Sophie.
So for Git, it's a version control system.
Awesome. Yeah. Duarte.
For source control, the act of keeping track of the history of our code.
Excellent. Yeah. Keeping track of history of code. Marcel?
For the branch, I would say I would like to add cool feature or messing around with the code.
Way to add new feature to code. Another in-person stack?
Hi. So for GitHub, maybe one choice of sort of hosting platform for a remote repo. Other options are like GitLab or Bitbucket.
Awesome. One choice for remote host for projects. I'll say for controlled projects. Also, see GitLab / Bitbucket. Ooh. You didn't see that? Charmy?
Hi. So for repository, it's a version control system that keeps tracks of all the changes you make to your files or your projects.
Version controlled project keeps changes. Awesome. All right. So we still need a definition for pull request. Any brave soul? Rakesh?
Yeah. Pull request, like mechanism for a developer who will notify all the member that certain features maybe happened or not.
Yeah, awesome. Way to notify developers that changes, particular changes. Yeah. So let's go through these one by one, and I'll just sort of add additional things. So Git, is a version control system. Some other examples are Mercurial. GitHub, yes, is one choice for a remote host for source control projects. So GitHub hosts all of the Git history and Git logs for your particular project. Source control, the act of keeping track of your history of your code. You can do this with a source control system like Git, or you can just do this by saying, like, naming one Word document version 1, naming another one version 1, final, naming another one version final, really for real, etc. Repo, is a version controlled project. So that's like one instance of version control, you can think about it, or source control. It also keeps track of all of the particular changes. Pull request is a way to notify developers of particular changes. And you can also think of it as like stages the commit or stages the changes in one branch to be pulled into another. My N key does not seem to be working. Commit, a change that adds a new note to a current branch. I'll add that you can think of it like an object, the way Jason said last time, with like information about who made the commit. Like an object that holds information about who made commit, changes involved. Branch is a way to add a new feature to the code. It's like a copy of it. It links back to the main branch in some way and might add additional changes. You might have changes added relative to main branch or other branches. And then clone is a local copy of the repo linked to remote. Yeah, great. I guess clone can also be a verb. So you can have a clone, or you can actively clone something. So the act of cloning something is creating a local copy of your repository that's linked to the remote. Cool. Thanks so much for participating, y'all. I really appreciate it. Okay. So I wanted to do that. I wanted to take a second to just stop and sort of pause on the vocabulary, because there is a lot of vocabulary, and I don't want it to sort of go by too fast. So yeah, let's keep going. Okay, so now I'm going to give you a walkthrough of how Gitflow works. This is a probably overcomplicated looking diagram of Gitflow, sort of officially defined. We're going to go through it step by step, and then, like I said, I'm going to give you a walkthrough of how Gitflow works. So just to orient you to a couple of features in this branch, we're using circles to represent commits in the same way that they were represented in Jason's last lesson. And then the lines here represent like adjacent commits. The blue top here represents the state of the main branch. Purple is another one called the develop branch, and then green are different feature branches. Okay, so the first step in Gitflow, in my workflow, is to start on GitHub and create a new repository. and then clone it to your local computer. You can also create a Git repository on your local computer and then add it to GitHub. Both are fine. I just usually start on GitHub for whatever reason. Next, once you have a clone of your repository, the very first thing to do is to create a develop branch. Having a develop branch is a way to protect the main code. So you basically make all of your, merge all of your changes from your feature branches into develop, make sure develop is working properly, and only when you're convinced that develop is working, then merge it into main. So that way main always has a working version of the code, and you never have to like merge in 1 or 2 branches at the same time to main. The next thing you can do if you want to make a change is to create a feature branch. So now we've got the main branch here, a develop branch that was built off of that, and a feature branch that was built off of main. So far, they're all exactly the same. They're just 3 copies of the same code. Now we can commit some changes. As Jason would say, type. We've got 3 commits here that were made. Now say someone else wants to create a different feature branch. They would also create the feature branch from develop, even if develop itself has had a couple of changes or commits made to it since the previous feature branch was made. You always want to create directly from develop. So now we might have 2 developers working on different feature branches, making their own commits at the same time. And this can also sort of repeat recursively. So if someone else wants to make a change to this feature branch, like based on this feature branch, they could create another branch based off of that one, or someone could create a 3rd branch based off of that branch that was created based off of that feature branch. So you sort of create branches recursively, like I said. All right, so let's say we finished our feature branch. Let's say we finished this one. You then push those changes to GitHub. So sync GitHub with your local Git history, and then create a pull request. So here, this is what the web interface looks like. You'd click new pull request here. Once you actually make a pull request, this is what the interface looks like. I'll also show you this in real time when I do the walkthrough. A couple things to point out. At the top here, it'll show you which branch is being merged into which other branch. So my pull request is pulling from, in this case, the Gitflow branch into the base branch, the develop branch. There are a couple of different tabs here that give you information about the changes that you've made. If you click on this tab, you can see the list of all of the commits that were made on the development branch. Sorry, on the feature branch. You can click on this tab to see all of the changes that have been made to the files that you're pulling in. So here's what that looks like. Green highlight means added code, and red means deleted code. There's also comments that you can make directly on the pull request. So if you're talking with other developers about this pull request, here's where you can look for that. And then there's also a list of all the contributors to the pull request. So once you've actually created the pull request, this is what it looks like. You can add your comment here. There might be several different comments making up the conversation about this. You can also ask for pull request reviewers. You can give it fun labels or projects, milestones, all sorts of fun stuff. It's generally good to be descriptive with your changes. People can, go through and see all of your commits or see all of the files changed. But generally, you don't want to make them look. You want to sort of provide a nice summary for them to see, so that they can look in. They have an idea going in of what changes you made. If you're committing to a package with lots of developers working on it, often an admin or senior developer will review and merge into develop after approval. So on many packages, the develop and or main branches are protected, so you won't be able to merge into them directly. You can ask for a senior developer to review it. Sometimes if you make a pull request, automatic checks will run. So there's a test suite. We'll talk a lot more about testing in 2 days. that'll automatically get triggered. And then finally, if you merge your pull request, we recommend that you delete the feature branch after merge. So this might sound a little scary to people, but remember that nothing is ever really deleted with Git unless you do git reset. If you delete your feature branch, it's not actually deleted from the Git history. It sort of, and all of the changes from this Git branch have been merged into your new branch at this point. So the Git branch, the feature branch doesn't necessarily contain any additional information at this point, and it's still in the history, so it's good practice to delete it. All right, so at this point, we've merged the changes from our develop branch, from our feature branch into develop. So up to this point is what the code looks like. Then if you've made a sufficient number of changes to develop and you're convinced that develop is working well, you can make another pull request from develop into main and merge it into main. Generally, whenever in Gitflow, whenever you make a change to main, we'll release a new version as well. So if you add version 0.1 over here, then you might release version 1.0. We'll talk tomorrow about how to actually do version releases and things that you need to do to make your code installable on pip, etc. So don't worry about that for now. Okay, so let's do a demo. So I'm going to show you the process from start to finish of creating a new repository and adding to it using Gitflow. All right, so let's go to GitHub. GitHub autocompletes to overtypes for me. All right, so I will make a new repository. Okay, suggestions for repository name. Type in chat. Sorry, in-person people. Snoot, I love it. You heard me. All right, I'll add a README file. A gitignore file is a file that tells Git which files should not be kept track of in the source control. So for example, if you, like one standard thing to add is any file that ends in .pyc. These are compiled Python files and they're specific to your machine. So it's not useful to add those to your Git repository because they're not going to be useful to anyone other than you. So if you add a gitignore template, it'll automatically add some common file enders to ignore. I generally add it for Python unless you're planning to code unless you're planning for the majority of your code in your repository to be in a different language. You can also choose a license. We'll talk a little bit more about that tomorrow. For now, I'm not gonna license Snoot. You know, it's all right. All right, I'm going to create repository. All right, Snoot, you heard me. It's real. Now, the next thing I'm going to do, so this only has one branch right now. It's just main. So the first thing I'm going to do is to create a develop branch. I'm going to clone the code to my local computer. I think I'm just going to share my whole desktop. All right, so I'm going to open up. So this part where I clone, I generally do in terminal. So I'm working on a Mac. I'm just going to open up my terminal. I'm going to cd to wherever I keep all of my, wherever I want to put this. On my computer, I keep all of my GitHub repositories in this document/GitHub. So I've got a bunch here, and you can put them wherever you want. I'll do git clone, and then paste the name of my Snoot repository. We have clone Snoot, ls. There it is. All right, so let's go in. You can see I've got the README here. Okay, so now the first thing I'm going to do in Gitflow is to create.
Sarah, can you make your text a little bigger? Just
Oh, yeah.
zoom in on your terminal.
Yeah.
Make the terminal bigger and then zoom in also. Yep, great.
Cool. Thanks for the suggestion. Okay, so at this point, I generally transition to working in VS Code. So I'm gonna, now that I've made this bigger and you can all see it, I'm gonna X out of it. I'll open up VS Code. I'll open. I go to my documents, GitHub. I don't really play League of Legends, don't believe me, I'm not that cool. All right, sweet. So here's Snoot, here's our README, here's the git ignore. So it's got a bunch of stuff that Git is gonna ignore. This was automatically populated by GitHub. Here, down here, shows you what branch I'm currently on. Okay, so as I've been threatening for a while now, I'm gonna make a develop branch. Click on here. I'm going to click create a new branch from, which means I get to choose the base branch that I want to create my new branch based off of. I'm going to make my new branch called develop, and I'm going to make it based off of main. Okay, so now I've got develop. This little button now is telling me if I click it, I can publish the branch. So currently, my develop branch on my local computer is not, GitHub isn't aware of that. It's not synced to GitHub. So if I go back to GitHub, you can see, even if I refresh, it still says there's only one branch. It doesn't know about develop yet. If I want to make it know about develop, I can click publish branch. Now it's synchronizing the changes. And now if I go back here and refresh, now I've got a develop branch as well. There are two branches. Okay, so I want to change Snoot. I want to add some functionality to it. So let's add a feature branch. I'll use the same process, create a new branch. Let's call it, what should we, suggestions, what should we have, what should we do with Snoot? Boop. Yes! Oh my God, amazing. Wow. I told you I love this community. Okay, add file to boop Snoot. So this is silly, but there's a best practice that I'm showing you how to do here, which is that generally you want to make your branch names very specific. So it's hard to do this sometimes. You don't always do it, but in general you want to make them active, like what you are adding or what you are changing, and then be specific about what you're doing. You also generally want to keep your feature branches small and self-contained. So big pull requests are not great. We want pull requests to make small changes at a time. Okay, and I'm going to build it based off of develop now. Okay, so now I've got 3 branches. GitHub doesn't know about my branch add file to boop Snoot yet. And they're all copies. Okay, so now I'm gonna finally make some changes. So up here, there's a little button to make a new file. So let's make a new file. I'll call it boop Snoot. Snoot.py. Okay, so how do we, if Snoot equals, no, I'm not saying if Snoot print boop, else print no. And of course, let's say Snoot equals true. Okay, great. I've got an excellent, very useful program. So let's add or stage the changes. Actually, I'll make another file so I can show you the adding individual versus adding all files. So So let's make another file. I'll call it super boop snoot.py. If snoot print super boop, else print super no. And of course, snoot equals true again. Okay. So now we've got two files that have changes. If we want to add all of the changes, we can click this button on the top, and that stages both of the changes. I can also unstage all of them. Also, if I want to make a commit with just one of these changes at a time, I can just stage the changes in this file. Let's do that. So add file to boop snoot, and then I can commit that. And then let's make another commit. Add file to super boop snoot. Add and then commit. Did I click that? There we go. If I open a terminal and do git log, you can now see the chain of commits that I have. So this commit added a file to boop snoot. This commit added a file to super boop snoot. Okay, so I haven't published this branch yet. GitHub doesn't know about all of my snoot booping, but let's do that. I can publish the branch either here or here. I'll click here. Let's publish it. All right, so now if we go back to GitHub, whenever you make changes, you'll see this little pop-up-y thing notify you that you've got some recent changes. You can make a pull request. You can also do that by just going to your branches and make a new pull request there. You can also go to the pull request tab. There's lots of different ways to make a pull request on GitHub. Let's do it this way. We'll do a new pull request. So we need to choose the branch we want to pull into the other branch. So since we're following Gitflow, we only ever want to make pull requests into develop. And then we're going to go from add file. I guess it should have been add files to boop snoot. Oh well. Into develop. It shows you the chain of commits that I've made. It also shows you all of the additions, the changes to the files that I've made. Now let's create a pull request. Who should we have to review? Oh, no one's a collaborator. Oh well. I was going to make Jason review it, but that's okay. I'll add a description. Maybe I'll say add files to boop snoot. First file added oops snoot. Second file added super boops snoot. Create a pull request. Then it looks like this. You can still look at the commits if you want, or look at the changed files. If I want to add another comment, I can do that here. Okay, let's just merge the pull request. Confirm the merge. And I can delete the branch. So now if I go back to my code, still got two branches. It'll notify me that develop had recent changes. So once I make several changes to develop, I can then merge those into main. So I won't do that because it looks basically the same. All right, so that is the end of the demo. I'll leave you with a summary of the processes to add a feature. First, you want to pull the latest code from the develop branch. Then you want to create a feature branch from your develop branch. Make your changes, stage, commit, and then push to GitHub. And then finally submit a pull request on GitHub and merge into develop. Once you've done that enough times and you have enough features added into develop, then make a pull request from develop into main. The only part of this that I haven't showed you is pulling the latest code from the develop branch. So let's go back and I'll show you what that looks like. So now I'm currently still on this add file to boop snoot branch. Let's go back to the develop branch. I can just click on that and just click here, develop. And then you'll see here, there's this little notification that there are 3 commits on the origin develop branch that aren't synced with my local copy. Those 3 commits are the 2 commits that I made on the add file to boot snoot branch, and then the additional commit that I made to merge that pull request into develop. So if I click on this button, it'll synchronize the changes. You'll now see, now that I'm on the develop branch, but I've got all of these changes from the add file to boot snoot branch. So that's all you need to do in order to pull in the latest changes. Now, if I want to make a new feature branch, add more changes, I can follow the same process, create a new branch from the develop branch. Alrighty, I think that's it. Okay. Any questions? I haven't been following the chat super well, so if someone has a question, please let me know. Okay, sounds good, y'all. Oh, there's a question. Is GitHub pull request the same as git merge? Effectively, yeah. It's going to do the same thing under the hood. GitHub pull requests have additional features to like notify people. It's also it's a public thing, so it's happening on GitHub. So you're doing the merge on GitHub rather than just on your local computer. But you can also make merge branches on your computer and then publish the changes to GitHub as well. So it's sort of like just doing a public merge. Would you ever just do a merge on your CPU before doing a pull request? Yeah. So one example is if there are changes to if there were changes to develop that you wanted to merge into your feature branch. Sometimes I'll do that on my own computer. So I'll pull in the changes to develop and then pull those changes from develop into my existing feature branch. Then I'll create a pull request on GitHub. So the change is that the chain of changes is that I created a feature branch, someone else created a feature branch, they pulled their changes into develop. So develop now has additional changes that my branch doesn't know about. The workflow that I generally use is that I will sync the changes from develop to my own computer, then merge those changes into my existing feature branch, and then make a pull request. You could also do that on GitHub. It's just sort of my preference. 2 people write code by themselves and publish different branches. Does merging branches create a superset of files from those branches? Yeah, so you're saying like, if I create a feature branch with a new file and someone else creates a feature branch with another new file. Okay, so yeah, so there are several things that could happen. You could merge those branches into one another, in which case, yeah, you would create a branch that has both of those new files. Another thing that could happen is if I create a new branch, say I have one feature branch with one new file, one feature branch with another new file, I could then merge the first branch into develop. So then develop only has one new file, and then merge the other feature branch into develop afterward. So then we sort of have develop, it gets one new file from one branch, then another new file from another branch, and then you end up with both files. Does that help? Yeah, thanks for the explanation too, Simon. Yeah, good comment. Yeah, so git pull is the command to fetch the changes. So make your local copy of your Git repo aware of the changes that have happened on GitHub, and then actually add in those changes. So merge those changes into your local copy. Origin, yeah, good call, David. So origin means the remote copy of the Git repo. So the version of the Git repo that exists on GitHub. Yeah, feel free to add that to the glossary as well. Another question, branches are best when we're working on adding features in separate files, right? Like we shouldn't edit the same file on 2 different branches. Yeah, so it's sort of it's yes and no. There are definitely situations where folks might be working on the same file and adding different things to it. Especially if you have like really big files, maybe folks are working on different parts of the same file. Also, sometimes people are working on the same parts of the file. And in that case, it's actually really good to use branches because you want to be able to keep track of and visualize the difference between the changes that you're making. It's also, GitHub isn't, Git and GitHub aren't a replacement for communicating with your collaborators about what changes you're planning to make. And it's of course really good to talk to someone and say, I'm planning to make these changes to this file. Are you going to make changes that might cause merge conflicts? So you don't necessarily want to be, making changes on different branches that are going to be causing different behaviors or that are maybe you want to make sure that you're not actually, making the same changes, for example. But if you are, trying to add 2 different functionalities to the same file, it is helpful to use Git branches so that you can separate out those changes. Yeah, great questions, y'all. I think in the interest of time, let's stop for now and take a little break. But please keep the questions coming on Piazza or Discord. This has been really great. All right.
Okay, so we'll get started again and finish today with debugging. We are a little short of time, so we'll do as much as we can in the last 35 minutes. But but all the material are online here. So so if you go into our GitHub code Astro repo into the day 2 folder, you'll see all of our material in our README at the bottom, and here we'll be doing the debugging lesson. So we go here. This is the debugging lesson. So I'll take a brief moment to appreciate the meme. All right, so this is mainly going to be kind of a hands-on demonstration. So there's very few like principles or methods of debugging. I'll cover a little bit at the end as a few tips and tricks, but generally it's I'm just wanting to show you how we can do some debugging in VS Code that might assist you beyond just doing like say print statements and things like that. So that's what the goal of today will be. So I've opened up VS Code here. I'm in the day 2 folder. So if you go back to our day 2 folder, there's a couple of files that we're going to access. The first one is going to be my demo file is the debug matrix.py. And then for the activity, we're going to work on broken orbitals. So first we're going to go to the debug matrix. So I'm opening it up in VS Code. So this is the debug matrix file. So this code is broken. The goal of this is to generate some random pixel art, but you'll see that it's not going to work. So in my terminal down here, if I can't see myself, I have too many things. I'm using the share screen to type. So this is going to be something. All right. If I try to run this file, you'll see that it'll crash. Be like, oh no, it crashed. And then now we have to begin the debugging process. So I'm going to show you some nice things about VS Code that kind of assist us in this debugging process. So we're going to use the VS Code debugger. So here on the left-hand side panel, you've seen the file explorer, you've seen the source control that Sarah demonstrated. Now we're going to try to use the run and debug feature of VS Code. So to do this, you have to have a debug setup. I'm going to show that later on, but basically we have a debugging setup already set up. It's set up to debug the current Python file, and this is generally all I use. I don't have any answered debug setups in this. More enterprise environment in like a company, you might have more, but here, this is basically gets me through 99.9% of all debugging situations. So I'm going to run this little green play button, and it's going to run my code debug matrix in debug mode, which I briefly demoed yesterday. You'll see that this is going to run, and when the exception occurs, it's going to stop the code and basically allow me to debug starting from here. So here you can see that an exception has occurred, and I give a value error x, setting an array element with a sequence. Just a caveat, these are extremely contrived bugs because it's really hard to write your own bugs into the code. So let's see. One of the nice things about this is now I can like hover over in debug mode, hover over all these variables. So I can see what these variables are, the current state of them. I can hover over j is 0, I is 0, so RGB is like this. So you can see that basically I'm trying to set new image ij equal to pixel RGB. So what are new, so we can actually evaluate some of these. So when you're in debug mode in VS Code, you can use the debug console. And what the debug console allows you to do is to type basically arbitrary code down here, and it will execute them as we right now in the current state of the code as when it crashed. So I can type new image, I really can't see, it's j comma I, and I hit enter. That's 0, and I can type what pixel RGB is. So instead of doing print statements, we can do prints on the debug console. It's a little bit more elegant. It's a little bit more flexible. So you can see that pixel RGB is a tuple with 3 elements. So we're trying to set this thing equal to 0. So obviously that's not going to work. So there's something going on here. What we can do, it's a little contrived. Maybe you can already see how to solve this, but I'm gonna just demo some other features. We can maybe say, let's say, oh, we don't know what's going on. Let's just step through the code and see what's going on. But maybe we don't want to run every line of code. So what we can do is we can set what's called breakpoints. So this is basically a this itself is actually a breakpoint. So the fact that an error has occurred basically is a breakpoint that the system will stop when an error has occurred. And that breakpoint is enabled by enabling this check mark in the bottom left here called uncaught exceptions. So anytime the code basically throws an error and no one is able to handle this error, it will automatically stop the code there and let you debug at that step. I can also set my own breakpoint. I can just say, if you hover over the code to the left, the line numbers, these red buttons are showing up, and you might be interested in pressing them because they're red buttons. So you can press one of these and you will set a breakpoint. So what happens is if I stop the debugger and I run it again, notice this breakpoint is set before the code crashes. So I can run it again, it will stop at this breakpoint. So basically the code will run, it will run all the lines up to that line. So this line is now, the highlighted line is now the next line to run. This line hasn't been run yet, but I can basically prepare to run. So you can see that the new image, like go into the debug console and try to type new image, it'll be like this hasn't been defined because it hasn't been run. But dim and dim2 have all been defined because they've been executed in the line before. And now I can actually step through my code. I can use things like, so here at the top, you have a little control panel for stepping to operate the code in debug mode. So I can step through the code line by line by use the step over button. So I step over the button, it will execute each line of code one at a time. So now, if I type new image, now a new image has been created because we stepped through that line. So I can keep doing this line by line and basically run the code until it crashes, and there it crashes. So one thing you'd be like, maybe there's like, let's understand what's going on in this sub function, generate RGB pixel. I can restart the code, restart the debugger, and it's gonna, again, run until I hit the first breakpoint, which in this case is gonna be this red button again. And here I can keep using the step over function until I get to this line. This line, pixel RGB equals to generate RGB pixel, is now the next line that's about to be run. And I can use this step into button to basically step into that function. It's gonna basically, instead of stepping over it and evaluating it automatically, we can now evaluate what happens inside this function line by line. And you can do this recursively. You can go to each function that gets called by each function that you call, basically. So I can now step through this function and see what happens in this function. You can see that basically, for a given XY coordinate, I generate a red, green, and blue value. So that's all it's doing, and now you kind of understand what's going on in this code. So after you return, you can keep hitting step over, or you can hit the step out of function, and it will finish executing the rest of this function, step out of it, and return back to where you previously were. And you can continue, and your code will keep crashing. So maybe at this point I figured out enough to figure out how to fix my bug. I'm trying to set this is 0 equals to RGB value. Maybe I need to have more dimensions. So I can set this dimension to 3. I'm going to try running the code again. So I can remove this breakpoint. Like, I don't need that breakpoint anymore. I know what I'm doing. I can run the code again in debug mode. Oh, the code crashed again. This is the life of debugging. So you can be like, okay, I can set my debugger back up again, and I can restart the debugger. I'm just showing you some of these features. You can probably debug a little bit smarter if you think about some of these errors, but I'm just wanting to show some of these features. So I can now, again, step over, just like run through this for loop. Like, oh, it hasn't crashed yet. I'm going to now execute for j equals to range dim2. Like, oh, it hasn't crashed yet. Okay, so this can run basically forever, and maybe you're like, I'm tired of stepping over things. So I can actually set what are called conditional breakpoints. So I can make a new breakpoint here. But I can edit it to only stop when I want it to stop. So I skipped through this a little fast, but it basically crashed when I equals to 35, I think. So I can set the expression only evaluate this only use this breakpoint when I equals 35 is true. Hit enter, and if I hit this button called continue, it's going to keep running until it hits that breakpoint. It's basically going to keep running until I equals to 35 in this case. To here, so we've now skipped a bunch of I. We didn't have to cycle through j repeatedly and wait until when I equals 35. We've hit exactly when I equals 35, and j equals 0. We know this is about when the code crashes. This is one of these array indexing things. So if we print it out like new image.shape, like, oh, this is an array. This is an array of shape 105 by 35 by 3, and trying to access the second dimension and the 35th element is probably not going to work. Probably because I goes from 0 to range 105, and j goes from range 0 to 35, which means that we probably flipped I and j. So what we want to do is actually go j comma I comma j instead of j comma I. And now we delete all our breakpoints again, and delete them over here. Delete all our breakpoints, and then rerun it again without any breakpoints. Hopefully this works. We've created some art. So here now our code finally works. So we've generated some random pixel art. Can appreciate the pixel art, I guess. But mainly I just wanted to show you this to kind of demonstrate some of the features of the debugger. The fact that you can basically, the debugger can basically run and let you inspect the code when your code crashes, which is really valuable because instead of trying to anticipate what you need to print out, you can print out what you think you want to print out as when your code crashes. You can step through the code line by line, watch it execute line by line, which is like some advantages of having Jupyter notebooks. Like you can try out things like that. Is exactly what you can do with a debugger, but maybe on a more complicated system where you have maybe many Python files interacting with one another. So that's everything I wanted to show you on the debugger. I want to show you how to get the debugger set up, and with the time remaining, try to get you guys started on trying to debug something that you're totally not seen before. This is often what happens in astronomy. You get some code being like, run this code, and you're like, why is it not working? And trying to figure that out. So we have a debugging activity. So basically, there's an issue in Orbitize that we've raised, and basically I was just putting in random inputs to this Orbitize function called orbitize.kepler.calcorbit, and it was just returning all nans. Like, I don't know what I'm doing. I just input a bunch of numbers and it ran, but returned nans. So like what's going on? So that's what your task with investigating. If you have time, you can maybe investigate the full thing. Definitely, I'll say try to get the debugger set up and try to debug this code. So I'll show you how to do that. So your task is to debug Orbitize. To do so, you need to download a development version of Orbitize for the debugging activity. So we had you pip install Orbitize, which is like the released version. But typically, when you want to debug something, you might want to install a version from GitHub that you can edit yourself. You can type git clone Orbitize to get Orbitize. So here, oh, what happened? My terminal is broken. Okay, so if I go to, you can see that my GitHub is also similarly organized like Sarah's is. So I go here. I have my development origin Orbitize. So if I do this, you'll also get a git clone Orbitize. I'm not going to do it again because I've already cloned Orbitize, but I cd into Orbitize, then you'll see something like this, and then ask you to reinstall Orbitize. This will basically overwrite your system installation with the version you just cloned. So that way, if you make edits to the code, you can basically, if you make edits to the code, they will basically appear when you run the code. Again, I'm not going to run this just because everything's already installed. So that the next start is to set up the VS Code debugger, which is, I think, probably the more complicated thing. So to get the debugger set up, let me remove all the configurations in my debugger, and then I'll show you how to set it up from scratch. So I go here and just go delete, save. All right, so if you, with your brand new VS Code installation, go here and click on the run and debug section, you'll see something like this because you have no debug environment set up. There's a run and debug button, but actually click on the thing underneath it called create a launch.json file. So if you create this basically allows you to create a debug configuration. And if we go down to this button that says add a configuration, and you can pick Python, and then you can pick Python file debug the currently active Python file. And this will automatically create a debug configuration for you. If you hit save, now you see that I have a debug configuration I can play with. I recommend adding just one extra line to this configuration file because it will probably help you with some pathing errors. And that one extra line is this. I'm just following the instructions here, but not reading through it line by line. There's one extra line that is located in day 2 in the demo launch.json file. And that is this extra line called current working directory equals to file dir name. And basically, this allows you to run the file, assuming you're in the folder that the file exists in. So like basically you CD'd in your terminal to that folder and are running it from there. It just helps with pathing issues generally. So I recommend putting this in there in general. So now that I've had that, I can save it. And now I can go to my broken orbitize and close all these breakpoints, and I can hit debug, and it's gonna debug. It's gonna run orbitize in debug mode, and hopefully, yep, you'll see that RA, DEC, and RV all return nans, and this assert statement that everything is finite is false because everything returned nans. So we don't have a lot of time, so I would recommend to try to get the debugger set up and to be able to run, to get as far as I just did. So basically be able to run this debug.orbitize file that you see here in the day 2 folder, up to basically where you can use the debugger to run it and have it crash. That way, we're like almost there into the debugging process. If you have time, try to figure out basically which of the 8 inputs or 9 inputs into orbitize is causing the function to return nan, and identify at what line of the code in orbitize did the nan start appearing. And you can, if you get there, please report on Piazza what you find. So again, we have the same roles as normal. We have a driver and some navigators. So split into your project groups or in person to your partners next to you. So this anomaly will take longer than the time we have. So let's take about 10 minutes and get as far as you can, and then I'll reconvene and try to recap the rest of it. Is there a question?
Yeah, sorry, just a quick question from some folks on the Discord. Just confirmation for the debug configuration file. Is that being made inside the orbitize repo or inside the day 2 folder or broken orbitize.py?
It should be made wherever broken orbitize.py is. You can copy broken orbitize.py into the orbitize repo, or you can run it from the code Astro repo. Both will work. Just wherever that file exists, and you can access and run that file on VS Code. Thanks for the question. Okay, so we have 10 in 10 minutes to get as far as you can get, and then we'll you can work on it in the afternoon or at some other time in your leisure if you want to keep practicing with the debug mode. And then we'll try to reconvene at the end just to wrap up the debugging with some helpful hints. Okay, so yeah, let's go break into our groups, and yeah, we'll reconvene back in 10 minutes. Okay, should we
Jason, are you talking?
Okay, I did the muted thing, so I got to start all over. So I'm sorry. Sorry for the in-person people, for everyone. For I'm going to repeat it. So we're gonna have to wrap up the debugging assignment now. I know a lot of people didn't get as far as you might have wanted, but getting the debugging environment set up is kind of tough. So we'll be around on Discord, or in if you post on Piazza or have any issues with getting it set up, we can try to help you. It definitely takes a while the first time to get it all set up, but hopefully it'll be useful once you do it. I just kind of wanted to end with a couple of closing thoughts on debugging. Is that there's no really one process that is the full process for debugging your code. I think it's one of these things where the more you debug, the better you get. But I have a few bullet points here of things that potentially can help you. It's always important to establish what is working, and to establish basically your islands of sanity, and then work from there to figure out what else could be broken. Binary search or process of elimination is good. If you think you have a bunch of code, you don't know what part is broken, try to comment out the first half and only run the second half. If that part's broken, then only debug the second half, and then try to comment out half of the second half and work your way basically to try to narrow down what part of the code is actually broken. Now, Google is your friend that solves some things for you. I think the interactive debugger, like the one in VS Code, which helps you step through code line by line, helps a lot, especially if you're working on very complex packages, or many Python files that are interacting together all at once. And writing tests, which we'll talk about later this week, will help you a lot in developing Python packages that minimize the need for debugging. All right, so that's everything the debugging said. Sarah, do you want to close out day 2?
Yeah, so we made some closing slides yesterday, and I was a little delirious yesterday, not gonna lie, and forgot to do them. So let's do them now. Okay, so day 2 closing slides. So I just want to remind you all about all the different ways you can ask questions in the workshop. First of all, do it often. We would love for you to ask as many questions as you have popping into your head. If you're on Zoom, you can ask in the chat box. I'm going to remind you, everyone's been doing a good job of this, that we prefer that you don't unmute without raising your hand or asking in the chat box first. On Piazza, you can ask questions. I really love Piazza. There's an anonymous option as well. We don't quite have 5 minutes, but I'm going to give everyone an assignment to, if you haven't asked a question on Piazza yet, please ask a question sometime later today. It can be about anything. I'm sure there's something that's been confusing to you. If you're embarrassed to have your name attached to it, that's completely fine. Ask with the anonymous option. But yeah, ask a question sometime today. And then you can also ask questions on Discord, and this is the preferred way for you to communicate with your fellow participants. And just as a reminder, we're all going to be monitoring all of these mediums before, during, and after the lectures. So if you ask a question, we will try our very hardest to get it answered. These were the goals for yesterday, so I'll skip over them. One thing I wanted to say too is a lot of people write messages to me and Jason throughout this week, apologizing for something, apologizing for not being able to do an activity or having to leave the workshop early or not feeling like they are doing a good enough job. I wanna stop that. No more apologizing. This workshop is not for us. This workshop is for you, and you should use the resources and materials however is best for you. If you, by the end of this, only get through one lesson on day one, but you learned it really well, that is amazing, and I'm happy that you use the resources in the best way. I also want to remind you that we're not evaluating you. We're not going to give you a grade. We're not going to judge whether you completed everything. We just want you to learn. So don't apologize for learning in the way that's best for you. And also don't sell yourself short. Everyone here belongs here. You can all do this. And no matter what you come out of this learning, you will have come out of this learning something, having learned something, and that's valuable. Also want to remind you all again about the anonymous feedback form. A couple of you filled this out yesterday and today, and we really appreciate that. So please take some time this afternoon if you haven't already to fill it out. You can fill it out as many times as you want. You could fill it out every day of the workshop. You could fill it out several times a day if you want. Also keep an eye out for the recordings. We posted the recordings last night. We'll also post like a nicely formatted public version of the recordings later in the week. But for now, we've just got like the raw recordings for you to look at. And also the answer keys. I'll make sure I post the answer keys for the lessons yesterday and today tonight. So those should be up on GitHub soon. And yeah, have a great rest of the day or night, and I'll see you tomorrow. This is actually good.